Hi, greetings to lecture, Miss Yap. My name is Adrian Lim Jun Hong. So today, I'm here to represent my group, which is Group 3 in Section D17, to present the Deadlock Banker's Algorithm Safe State. So this is my group member, Stephen Ngu Chuan Ni, San Bao Chun, me, Lu Qi Xian, and Tae Yong Jun. So let's move on to our question. Consider a system with 5 processes, P0, P1, P2, P3, and P4, and 3 resources, A, B, and C. The following table indicates the maximum requirements and current allocation for these resources. So, this is our question table. The allocation here refers to what is the current resource that allocates to the process. And max here is demand of process. How many the resource the process need to complete the task. Alright, and the available table here. So let's move on to the first question. Determine the total instances for each resource. So in order to find the total instances, we need to use a formula which is total for each allocation plus available. So we need to create the new allocation table in order to let us more easier to calculate. So we create the allocation table, and we just copy the content from the question. So we copy down and we sum up together. So for resources A, the allocation is 9, B is 9, C is 6. So right here, 996 plus available. Available we can get it from the question, which is 1, 2, and 3. 1, 2, 3, and we sum up together, we will get 10, 11, 9. Right? So our total instances for resource A is 10, B is 11, C is 9. Alright. So let's move on to second question. Determine the need matrix for the system. So in order to find the value in need table, we need to use a formula which is max minus allocation. Alright, so for example, P0 here is 221. We need to refer back to the question. P0, we use max minus allocation, which is 4 minus 2, we get 2. 2 minus 0, we get 2. 1 minus 0, we get 1. So the need for P0 is 221. Right, 221. So the rest, P1, P2, P3, P4, we're doing the same thing. Just use max minus allocation. Alright. So we've done the second question. Let's move on to the third question. Use the safety algorithm to check whether the system is in safe condition or not. So in order to do this question, we need to use a formula which is need is smaller or equal to available. Alright, so we start from P0 first. P0, the need for P0 is 221, and the available here we're using 1, 2, 3. Alright, sorry this. So 1, 2, 3. After that, we need to determine this statement is true or false. So obviously 1 is not smaller or equal to 2, so the whole statement will get false. After that, we need to move on to P1. So we're using the same available 1, 2, 3, and we need to check again, is it true or false? So obviously it is false. 1 is not bigger or equal to 2. Alright, so after that we move on to P2, processes 2. Wow, and we're using the same available. So now, this statement is true because 1 is bigger or equal to 0, 2 is bigger or equal to 2, 3 is bigger or equal to 1. Alright, so this is true. So after we get the true statement, we need to update the available table. So why we need to update a available table? This is because we must imagine, alright, P2 already allocate this resource. P2 already finished the job and need to release the resources to the computer. Alright, so in order to find a new available, we need to use available plus allocation. Alright, so we have already have the available, which is 1, 2, 3, and we need to find the process 2 allocation. Alright, process 2 allocation is 2, 1, 0. So 2, 1, 0 plus 1, 2, 3, we get 3, 3, and 3. Alright, sorry. So the next question, we are using the new available, which is 3, 3, 3. Alright, so we use 3, 3, 3. And we need to determine again, is this a true statement or not? Yep, obviously it's true. So after that, we need to update 3, 3, 3. So what's the allocation for process 3? Process 3 is 1, 3, 1. Right, so 3, 3, 3 plus 1, 3, 1 will get 4, 6, 4. Alright, sorry. So after that, we move on to P4. So we're using the available 4, 6, 4. Is it bigger or equal to 2, 2, 3? Yeah. So this is a true statement. 4 is bigger or equal to 2. 6 is bigger or equal to 2. 4 is bigger or equal to 3. Alright, so true. We need to update the available table. So process 4 allocation, which is 1, 4, 3. Alright, so 1, 4, 3 plus 4, 6, 4, we get 5, 10, and 7. Alright, after we finish P0 until P4, we need to go back to the P0, process 0, and do it again with the new available content, which is 5, 10, 7. 5, 10, 7. And we need to check, is it correct or not? Yes, it's correct, it's true. Because 5 is bigger or equal to 2, 10 is bigger or equal to 2, 7 is bigger or equal to 1. Alright, so we update the new available table. So the process 0 allocation is 2, 0, 0. So we sum up together, 5 plus 2 will get 7, 10 plus 0 will get 10, same, and 7 plus 0 will get same, 7. Alright, so this is our new available. So moving on to the process 1, we're using 7, 10, 7. Alright, and this is a true statement also, because 7 is bigger or equal to 2, 10 is bigger or equal to 1, 7 is bigger or equal to 3. Alright, if it's true, we need to do it again, update the new available table. So we need to find P1 allocation, which is 3, 1, 2. So 3, 1, 2 plus 7, 10, 7, we will get 10, 11, and 9. Alright, sorry. So we can make a conclusion, which is this is a safe state, because after we doing the whole thing, we get back to P0 and P1, we still get the true here. Alright, so the current resource available, which is 10, 11, and 9. And the safe sequence for execution is P2, P2 go P3, and P4, and get back to P1, P0, and lastly is P1. Alright, so this is our safe sequence for execution, P2, P3, P4, P0, and P1. So the sequence like that. If it is 4, we cannot calculate as a safe sequence. We need to start from the true statement. Alright, so we get from P2, P3, P4, and P0, P1. Alright, so that's all for me. Thank you.